immense pleasure to extend heartfelt welcome to each one of you on second day of the workshop Alice in Quantum Land, organized by Indian Association of Physics Teachers, RC2, and Kanya Maha Vidyalaya, Jalandhar, Pioneer Heritage Institution of India. We are very much privileged to have Emeritus Professor Ajoy Ghatak amongst us to deliver a talk on the topic Understanding the Two-Hole Interference Experiment by taking into account the basic quantum mechanics. Now it's the time to introduce Honorable Professor A.K. Ghatak to all of you. वैसे सर किसी परिचय के मोहताज नहीं हैं. Ajoy Ghatak is former professor of IIT Delhi, currently Nasi Meghnad Saha Distinguished Professor. Professor Ghatak earned his PhD from Cornell University, USC, and also worked as a research associate at Brookhaven National Laboratory. He joined the IIT Delhi in 1966 and served until his retirement as an Emeritus Professor of Physics in 2007. Professor Ghatak received 2008 SPIE Educator Award in recognition of his exceptional contributions to fiber optics and optics education globally, and 2003 Optical Society of America Esther Hoffman Baller Award in recognition of his outstanding contributions to optical science and engineering education. He is also a recipient of S.S. Bhatnagar Award, International Commission for Optics Galileo Award, IETE Vadwa Gold Medal, Optical Society of India Amita D Award for lifelong research contributions in the field of optics. Professor Ghatak has made significant contributions to the field of optics and physics. He has organized numerous workshops and short courses and was president of Optical Society of India. Professor Ghatak has authored over 170 research papers and more than 20 books, including the widely used undergraduate textbook of optics, which has been translated into Chinese and Persian also. Now, it's the time to dive into the knowledge tank of Professor Ghatak. Over to esteemed resource person and great personality, Professor Ghatak. Over to you, sir.
Thank you so much. Can you hear me?
Yes, sir.
Achha. Let me share my screen. Yes. Can you see the screen?
Yes, sir.
Yes,
First
sir.
slide.
Yes, sir. It is visible. Yes, sir.
Yes,
You
sir.
can. And now I have gone to the second slide. Can you see that?
Yes, sir.
Yes, sir.
Okay. Let me put it in the slideshow mode. कैसे जाएंगे देखिए.
The F5 button, sir, from your keyboard.
हाँ वो तो नहीं मिल रहा है. एक से. हाँ. Sorry. Okay. Thank you very much for your very kind introduction. Dr. Neetu Verma, Professor Ahluwalia, and others had invited me. I understand that Dr. Neetu Verma is not well today. I'm so very sad to hear that. But I have about 50-55 minutes. I have prepared a talk on understanding the two-slit interference patterns experiment. I congratulate Dr. Neetu Verma and all her colleagues, and Professor Ahluwalia and all his colleagues at IAPT for organizing such workshops. Yesterday we heard Professor Arvind, and I myself learned a lot from that. And it told us the importance of the subject quantum physics today in numerous areas. It has applications in many areas. The above photograph has been adapted from the most beautiful experiment carried out by Tonomura and others. And this is the single slit interference pattern produced by electrons. And here you have about 10 electrons, maybe 1,000 electrons, 10,000 electrons, and more than 1 million electrons, something like that. So as the number of electrons, this is considered to be the most beautiful experiment in science. In 2002, Robert Crees, a physicist and professor of philosophy at Stony Brook University in the United States, asked physicists to nominate the most beautiful experiment of all times. And from that emerged a list of 10 most beautiful experiments in science. The 10th experiment, the last in the list, was the Foucault's pendulum, which demonstrated the rotational motion of the Earth. And you go to YouTube, and there is this beautiful video on YouTube where they show the slight rotation of the plane of oscillation of the pendulum because of the rotation of the Earth. And it was from this experiment that the rotation of the Earth, the spinning of the Earth around the axis, was established. The fifth experiment, you see, he listed 10 experiments. The fifth experiment on the list is the Thomas Young's interference experiment, demonstrating that light was a wave. And it was carried out by Thomas Young, and I will discuss that in 1801. And the first experiment, the top experiment, the most beautiful experiment is the double slit interference experiment with single electrons, which demonstrated quantum interference of single electrons. So that was done in 20th century. So we are going to discuss this experiment and the understanding of this experiment through quantum theory. So this is the book by Robert Crees, the 10, if you can read it, the 10 most beautiful experiments in science. In fact, I have also written a book with the same title. What Robert Crees has done is given the history, the beautiful history of the 10 experiments, how they were performed, when they were performed. What I have done is that in this book, a very thin book, is to describe the basic physics of the 10 experiments. In 1964, Richard Feynman, Nobel laureate, delivered 6 beautiful messenger lectures at Cornell University.
Dr. Ajoy, can you please shift this slide to second one?
ये slides shift नहीं हो रही हैं?
नहीं हो
नहीं
रही।
सर, पहले हो रही थी, अब नहीं।
Oh my God, यही मैं आपसे पूछ रहा था।
पहले हुई थी सर, अब नहीं हुई।
पहले हुई थी।
तो मैं देखूं क्या करूं तो फिर?
क्लिक इट सिंपली।
नहीं तो मैं क्लिक तो कर रहा हूँ।
अब हो गई। Now it is 6th one. Experiment 5th is showing.
हाँ, experiment 5th. अच्छा, तो मैं ऐसा करता हूँ, ये स्लाइड शो में कर देता हूँ, ठीक है। अब experiment 5 दिख रहा है?
5 is there. Yes.
Okay. तो मैं स्लाइड शो मोड में नहीं दे करके इस मोड में दे। तो the 5th experiment is in the list is Thomas Young's interference experiment, which demonstrated that light was a wave. And the first experiment on the list, the most beautiful experiment, is the double slit interference experiment with single electrons, which demonstrated quantum interference of single electrons. Now, this is the experiment that I'm going to discuss today. So, Robert Crees, if you can read this, can you see the cover of the book?
Yes, sir.
Achha. So the title of the book is The 10 Most Beautiful Experiments in Science. So it's a very beautiful book. It gives the history of the 10 experiments. What I have also written this book with the same title, but it has discussed the basic physics of the 10 experiments that I have mentioned. So in 1964, Richard Feynman, Nobel laureate, delivered 6 beautiful messenger lectures at Cornell University. And the first lecture was on the law of gravitation. And, I thought I will mention that in the 38th minute of his talk, Richard Feynman said, the law of gravitation is also used to calculate the prediction of planets' positions, which have great utility for astrologers to publish their predictions and horoscopes in magazine. And then he says with little anger, that is the strange world we live in, that all the advances in understanding used only to continue the nonsense which has existed for 2000 years. That means he does not believe this using Newton's laws of planetary motion to obtain the trajectory of the planets and then use them in horoscopes. So he never believed in astrology kind of thing. The 6th messenger lecture, which is really a brilliant lecture, and I would urge all students to hear this, was probability on uncertainty. It is this lecture that I will be discussing in great detail, the quantum mechanical view of nature. Feynman said that the interference experiment, the 2-slit interference experiment that we are going to discuss today, has been designed to contain all of the mystery of quantum mechanics, to put you up against the paradoxes and mysteries and peculiarities of nature. And then he says that I think I can safely say that nobody understands quantum mechanics. That this is what Richard Feynman said in around the 38th minute of his lecture. So quantum mechanics is very subtle, and we will discuss the solutions, the concepts behind quantum physics, which is considered as one of the most successful theories of 20th century. I urge all students to go to YouTube and search for Feynman messenger lectures at Cornell University and hear at least these 2 lectures, one on gravitation and one on probability and uncertainty. Many say that Richard Feynman, who was an American physicist, and Lev Landau, who was from the Soviet Union, were the last 2 physicists who knew everything of physics. Then there is this beautiful book on how to teach quantum physics to your dog by Chad Orzel. It's a very beautiful book on giving the basic concepts of quantum physics in a very humorous way, and in which Chad Orzel writes, as was mentioned by Professor Arvind yesterday, that modern life would be impossible without quantum mechanics. Without an understanding of the quantum nature of the electron, it would be impossible to make the semiconductor chips that run our computers. Chad Orzel further writes, without an understanding of the quantum nature of light and atoms, it would be impossible to make the lasers we use to send messages over fiber optic communication lines. And quantum theory's effect on science goes beyond the merely practical. It forces physicists grapple with issues of philosophy. So you see, so therefore, understanding, first of all, quantum mechanics is a subject which is difficult to understand, but at the same time, its importance is just too much. It is an extremely important subject for all concerned. And all my life, I have been trying to understand quantum mechanics, trying to teach quantum mechanics, and it has been a tremendous joy and pleasure to do that. And I'm still in the learning process. So this is going to be a simple talk, primarily meant for young students. As you all know, optics is a study of light which has fascinated mankind ever since he could see. So Newton was the first to say that he put forward the corpuscular model of light, and he wrote in his famous book on optics, "Are not the rays of light very small bodies emitted from shining substances?" And using the particle model of light, he derived what we now know as Snell's law. And then in the same century, around same period of time, Christian Huygens wrote a very beautiful book on light, and he put forward the wave theory of light. And he also derived Snell's law using Huygens, what we now do in our undergraduate courses, Huygens principle. So what is a wave? I'm trying to make things simple. I'm sure all of you know this. So if you hold a string, make it move up and down, then you generate what is known as an X-polarized wave. The displacement associated with the X-polarized wave is X of ZT is equal to cos kz. This equation defines a wave. This equation defines a wave. Why does it define the wave? Because you plot this at t equal to 0, and at a small time later, it has moved. So I can write down X of ZT is equal to so much, is equal to K if I take outside, then Z minus Vt, where V is defined to be equal to omega by K. So at t equal to 0, it is A cos kz, and at a slightly later time, it gets displaced. The whole curve, the whole displacement moves. The string does not move, but the disturbance moves in the distance v delta t in time delta t. So V represents the velocity of the wave. Similarly, I can have a y-polarized wave in which this is the x-polarized wave, and similarly you can have a y-polarized wave in which the displacement is of the string is in the y direction. You can have a circularly polarized wave, so that you rotate the string on the circumference of a circle and create what is known as a right circularly polarized wave, in which each point of the string moves on the circumference of a circle. If you rotate it in the clockwise direction, you generate a right circularly polarized wave, and if you rotate it in the anti-clockwise direction, you generate a left circularly polarized wave. For an electromagnetic wave, it is the field at a particular point, the electric field which rotates on the circumference of a circle. That is a right circularly polarized electromagnetic wave. It is so if a plane wave is propagating, then the field at a particular point rotates on the circumference of a circle. Now, so this is the stationary wave produced on a string, and it's a very beautiful experiment. If you go to YouTube and you write down the interference pattern produced by superposition of two waves, you will be able to see a very beautiful vibration of a string. So this is the principle of demonstrating the principle of superposition of waves. Now here I had an animation which I wanted to show you, that if I have two pins oscillating on a calm pool of water, then each pin will generate a wave, and the waves will superpose in each other to produce an interference pattern. There is a very beautiful animation that I wanted to show if it were shown on a slideshow mode. And the next slide shows the actual interference pattern produced from 2 point sources. Dr. Annapurni, if you just mute your photograph, because you are continuously moving around and I am sorry, thank you. So your photograph is continuously rotating on the screen. Sorry, thank you. So yeah, this is the actual interference pattern produced from 2-point sources vibrating in phase. So you have a calm pool of water, you have 2 sharp needles which are vibrating in phase, and each one produces a circular waves on the surface of the string. And if one produces a displacement like this, the other produces an out of phase displacement, then you will have a dark fringe. If they are in phase, then you will have a bright fringe. So this is the demonstration. This is the characteristic of the wave, that the waves will produce an interference pattern. So Thomas Young, although the wave theory was put forward by Huygens in the 17th century, but Newton's corpuscular theory was prevalent. No one really believed in Huygens wave theory until Thomas Young carried out this beautiful experiment using 2 pinholes, and he allowed monochromatic light to fall through, and he saw interference pattern on the screen, from which he could calculate the wavelength of light. So it was in 1801 that Thomas Young carried out this beautiful experiment which demonstrated the interference of light. Dr. Ankit Verma, if you can switch off your photo, please, because you are talking and it is disturbing me. Thank you. So if you have, this is from the 2-hole experiment with bullets, which is very beautifully explained in the Feynman lectures. You have a gun which emits tiny particles, say tiny bullets, and it is very beautifully discussed in the Feynman lecture that I had mentioned, and also in his book, in volume 3 of his book. And if you have a 2-hole experiment, then the bullets will either go through hole number 1 or hole number 2. So if hole number 2 is closed, then you will get an intensity pattern on this, which is P1. That is, only bullets through the hole number 1 will pass through. And if hole number 1 is closed, then you will get the intensity pattern like this on the screen. If both holes are open, then the bullets will either pass through hole number 1 or hole number 2, and you will get the sum of the intensity pattern. On the other hand, as I had mentioned just now, if you have a wave source, then the wave will pass through both the holes, as I have demonstrated in the previous slides. They will interfere and will produce an interference pattern. So Thomas Young's experiment proved that light plus light can produce darkness, and it demonstrated the interference pattern. And so therefore, the wave theory of light was established. Wave theory, and as you all know, the diffraction of light and polarization of light was deeply studied. But no one knew what was waving, what was the displacement associated with the wave. So people say there is a book by Andrew Robinson that on Thomas Young, and Thomas Young is said to be the last man. He was a medical doctor, the last man who knew everything. Then, although the wave nature of light was established, people did not know what is the displacement, because light can pass through vacuum. The light that comes from our sun passes through vacuum. So what is the displacement that is associated with the light wave? So that was established by Maxwell. So light was a wave that was established, but how could it propagate through vacuum? So I had an animation here, which unfortunately I'm unable to show. It was answered by Maxwell. As most of you would know, that around 1864, Maxwell predicted the existence of electromagnetic waves and said that light itself is an electromagnetic wave. So when a light wave propagates, associated with it is an oscillating electric field, and the oscillating electric field generates an oscillating magnetic field, and the oscillating magnetic field generates an oscillating electric field. That is how the electromagnetic waves propagate through empty space. the concept of the electric and magnetic fields was put forward by Faraday. You see, before that, for example, you have Coulomb's law, that two charged particles will attract each other or repel each other. But that the charge will produce an electric field, that was put forward by, it's a very subtle concept. Today we take it for granted, but it's a very subtle concept that there is a field associated with it, which is present even if there is nothing there. So there is electromagnetic, the light coming from the sun, through the sun, from the sun is through the free space, through vacuum. And there, because of the light, there is an electric field there. So if there was a charge, this electric field will exert a force on that charge. The laws of electricity and magnetism are governed by Maxwell's equations, and one says that God said, let there be Maxwell's equations, and there will be light. So this is the entire electromagnetic spectrum, from gamma rays to X-rays to ultraviolet to infrared to microwave and the waves that you receive on your cell phone. They are all electromagnetic waves. And only difference is they have different frequencies or different wavelengths. X-rays and gamma rays have very small, very large frequencies, and the radio waves have this smaller frequency. The visible region of the spectrum occupies a very tiny portion of the entire electromagnetic spectrum. And all wavelengths, whether it is gamma rays or X-rays or the blue region or the red region, they all travel. Light travels in free space, in vacuum, with an identical velocity. Vacuum is a non-dispersive medium for light waves with an identical velocity of 299,792,452 meters per second, about 3 into 10 to the power of 8 meters per second. Now, after Maxwell, Heinrich Hertz carried out this experiment. You can see the similarity of this experiment with the string experiment that I had shown, the vibration of the string. He created stationary electromagnetic waves by allowing electromagnetic waves from an antenna to fall on an aluminum screen, then getting reflected and producing standing waves. Using this, he could calculate the wavelength, he knew the frequency, and therefore he could calculate the velocity. And he found that the velocity of these electromagnetic waves was also 3 into 10 to the power of 300 million meters per second. So therefore, the electromagnetic theory got very quickly established, and the reflection, refraction, and everything was understood using electromagnetic theory. So Max Planck later said, Maxwell's theory remains for all time one of the greatest triumphs of Maxwell's theory remains for all time one of the greatest triumphs of human intellectual endeavor. Then in 1895, because Maxwell's theory was so successful, Lord Kelvin had said that there is nothing new to be discovered in physics now. All that remains is more and more precise measurement. Then came Einstein. Einstein was working in the Swiss Patent Office, and the year 1905 was Einstein's Annus Mirabilis, Year of Miracles. And in that paper, he published 5 outstanding papers. Which changed the face of physics. There's a beautiful book by John Stachel, which the title of it is Einstein's Year of Miracles. That is 1905, when he was not in a university, not in a big laboratory, but completely isolated in a Swiss patent office, where he worked day and night, and he produced 5 papers that changed the face of physics. That was 1905. But it took a long time for him to get the Nobel Prize because of the politics that is involved in the award of the Nobel Prize. And so 1905 was Einstein's Year of Miracles. In the second paper, or in his Year of Miracles, Einstein wrote that radiation energy, that is light, consists of indivisible quanta of energy. That is, light consists of packets of energy. And how much is that energy? That is equal to the Planck's constant h times the frequency. In a later paper, Einstein himself had said that these packets of energy also have a momentum equal to given by h nu by c. So this was in 1905. Everyone believed in Maxwell's wave theory. So no one really believed in Einstein's quanta of energy. And he then explained photoelectric effect. I'm sure all of you know what is photoelectric effect. Incident ultraviolet light, when it is incident on a photoelectric surface like sodium or cesium or potassium, photoelectrons are emitted. The maximum kinetic energy is given by h nu, which is the energy of the photon minus a constant, which is characteristic of the metal. So this is known as the Einstein equation. And this was verified in 1914 with a remarkable degree of accuracy by Robert Millikan, for which Robert Millikan also got the Nobel Prize. So Einstein in 1921, by that time, he had discovered the special theory of relativity, his famous equation E is equal to mc square, his general theory of relativity, his theory of stimulated emission. But he had great difficulty. No one would like to give him the Nobel Prize. Some people say because he was a Jew. And eventually, in 1922, he received the 1921 Nobel Prize in Physics, not for his theory of relativity, but for this equation, not for the concept of the light quantum. Today, we know that the light quantum is known as the photon. So he got the Nobel Prize for this equation. So who discovered wave-particle duality? Wave-particle duality was discovered by Albert Einstein in 1905 when he put forward the corpuscular model of light. Now, going back to the same era, J.J. Thomson, as you all know, discovered the electron. And now we know that the mass of the electron took 10 decimal places and 9.10 so much into 10 to the power minus 31. The charge of the electron, it can be bent by an electric field or a magnetic field. So on the back of our mind, we visualize the electron as a tiny particle, speck of matter. Then in his doctoral thesis, Louis de Broglie in 1924 predicted, the experiment was done later, that you must remember, that the experiment was done later. Louis de Broglie, in his doctoral thesis, said that the momentum of the photon as given by Einstein was equal to h nu by c is equal to h by lambda. So he said that if this relation is valid for a photon, for a light quantum, at that time it was known as the light quantum. The word photon was introduced in the year 1926. So this must also be valid for electrons. So he said that electron must also, notice the year, it was 1924, not 24. He said, he predicted, it's a beautiful paper, and he predicted that electrons should also demonstrate wave-like properties, and with the wavelength given by h by p. So it was only in 1926 that the wave nature of electrons was experimentally established by Davison and Germer in USA and G.P. Thomson, son of J.J. Thomson, in England, and for which they got the Nobel Prize. So here is the diffraction pattern by aluminum foil produced by X-rays and produced by aluminum foil, produced by electrons. So notice the similarity in the diffraction pattern. So, diffraction phenomenon is based on wave theory. So therefore, electron also through this experiment demonstrated the wave-like property. So earlier, Einstein said that light, which was known to be a wave, has a corpuscular property. Davison and Germer and Thomson demonstrated that electron, which is known to be a particle, also demonstrate wave-like properties. So the question is the electron or a proton a wave or a particle? Now, some books write that it is sometimes a wave, sometimes a particle. Some people have given the name wavicle, sometimes a wave, sometimes a particle. That answer is incorrect. So the correct answer is that Feynman very beautifully writes and also mentions in the Feynman lecture that they are neither waves nor particles. Not a wave hai, na particle hai. So I have really not answered the question that whether the electron is a wave or a particle. So the correct answer is they are neither waves nor particles. Then you will say you have not answered the question. So what are those? Hai kya cheez? So the answer to that question is that they are described. The electron is described by a wave function, which is the solution of the Schrodinger equation, which was put forward by Schrodinger in 1926. I cannot measure psi. Psi is in general complex. So understand this, that what is therefore an electron or a proton or a neutron or an alpha particle? It is neither a particle, na to wo particle hai, na to wo wave hai. But it is described by the wave, by this Schrodinger equation. And where did we get that equation from? The answer is nowhere. It is not possible to derive it from anything you know. And Feynman very beautifully writes, it came out of the mind of Schrodinger. In this slide, I have tried to convey to you a very important message. That first, the electron or the proton is neither a wave nor a particle. It is described. So what is it? And I will now try to analyze a few experiments. It is described by a complex wave function, which is the solution of this equation. And the obvious question that you will ask me is, equation aapne likh kaise diya? How did you write that equation? And the answer to that, Schrodinger writes that where did we get that equation from? The answer is nowhere. It is not possible to derive it from anything you know. It came out of the mind of Schrodinger. It's a beautiful thing. But every book has a way to get the Schrodinger equation. So that is not rigorous. And so Schrodinger equation cannot be derived, but there is a heuristic derivation. Everyone gives there is some flaw in that argument. I will also give you a derivation that I consider a plane wave. Now, a plane wave, as you know, is given by cos kx minus omega t, and usually write it in the exponential form. And then you use the de Broglie relation and the Einstein relation. The de Broglie relation is that P is equal to h by lambda. I multiply and divide by 2 pi, and I get h cross, and 2 pi by lambda, I write k. So I write k is equal to P by h cross, where h cross is equal to the Planck's constant by 2 pi. And also I have the Einstein relation, E is equal to h nu, that is h by 2 pi into 2 pi nu, which is h cross omega. So omega is equal to E by h cross. So I substitute for k and omega here, px minus et. And then for a free non-relativistic particle, E is equal to p square by 2m. So I write the wave function as psi of a px minus p square by 2m into t. So I write that. This is the wave function. I say that it describes the electron with a momentum p. I differentiate once with respect to time, and I get p, so I get p square by 2m into psi, and then I differentiate twice with respect to x. तो p by h cross का square आएगा, p square by 2m. I divide by, multiply by minus h cross square by 2m. So I get p square by 2m psi. So I have written this equation. It's a heuristic derivation. It is not a rigorous derivation. Hand waving argument. And there is no rigor. And then I get this equation. And I take this as my Bible. Then you say that this is how, with a large number of loose arguments, I've been able to get a wave equation. And this, I say, will describe the electron. So I will assume that this is true. And I will tell you that don't ask me how I have got this. Don't ask me how to do. So now, for different situations, I will solve this equation. So how do I solve this? I solve this that by the method of separation of variables. So I write down psi of xt is equal to psi of x multiplied by t of t. And I substitute it here. And the variables have indeed separated out. I substitute this here, divide by capital psi of xt, and I get this is equal to this. But this is a function of time, and this is a function of x. So both must be equal to a constant. And I put that constant, where p is just a constant, where p can be any number between minus infinity and plus infinity. And then this equal to this will give me one equation, and this equal to this will give me another equation. And by solving those equations, I will get this. Of course, I will get this, because this is the equation that I had used to derive this. So this is the solution. This is a solution of the Schrödinger equation. So what I have tried to do is the following. For a free, non-relativistic particle, free means no potential energy function. The wave function is given by this. I have solved the Schrödinger equation. I say that it is described by this equation. Do not ask me how I have got this equation. And now I solve this equation. And I find that p can take any value between minus infinity to plus infinity. And so therefore, the most general solution is given by this, a superposition. Let us suppose sin x and cos x are solutions of a differential equation, then a linear combination of them is also a differential equation. So since all values of p are allowed, so therefore the most general solution is this. And then Max Born gave a very beautiful physical explanation of that. And that is discussed in any book on quantum mechanics, including my own, everywhere, that mod psi square of dx represents the probability of finding the electron between x and x plus dx, and apx square dpx is the probability of finding the x component of the momentum of the electron between px and px plus dpx. So what I have done is the following. I'm addressing the students, that I have written down the Schrödinger equation. I have said that don't ask me how I have derived it. I have somehow derived it. Then I take that as the ultimate truth. The entire non-relativistic quantum mechanics, a major portion of that is just the solution of the Schrödinger equation, which cannot be derived. A major part of non-relativistic quantum mechanics, of course, the spin of the electron you have to put from outside. is just the solution of the Schrodinger equation, actually the three-dimensional Schrodinger equation. And so this is for a free particle. This is the most general solution of the one-dimensional Schrodinger equation. And what is the physical interpretation? The physical interpretation is that I have not proved, but that can be proved very easily. Mod psi squared dx represents the probability of finding the electron between x and x plus dx, and apx squared dpx is the probability of finding the x component of the momentum of the electron between px and px plus dx. So now, how do I solve this? So I put t equal to 0. So if I know psi of x comma 0, then I get this. Then I can, if I know psi of x comma 0, then I can use this inverse Fourier transform to calculate a of px. और उसको यहाँ पर लगा देंगे. If I put it here and then integrate, I will be able to carry out the evolution of the wave packet. Evolution of the wave packet. Now let me do some experiments. So once again, let me repeat. Most of you would know this, but this for the students, that this is the most general solution of the time-dependent one-dimensional Schrodinger equation for a free particle. How do I solve this? So I write t equal to 0. If I know the wave function at time t equal to 0, then it is given by this integral. This is a Fourier transform relation. So a of px is given by the inverse Fourier transform. So let me now do some experiments. I have a single electron or an electron beam coming in, arriving at a slit. So at t equal to 0, it passes through the slit somewhere around the slit, so that it is somewhere around here. So I describe that that the wave function is given by 1 over under root of b and 0 everywhere else, so that 1 over under root of b sort of normalizes this wave function. I substitute it here and calculate a of px. This is 0, ये 0 है for x mod x greater than b by 2. So the integral becomes 1 minus b by 2 to plus b by 2 multiplied by this exponential integral. You can easily calculate this. If you do this simple calculation, you get sine beta by beta. And so therefore mod apx squared dpx, which is the probability of the electron acquiring a momentum between px and px plus dpx, becomes this. This is the single slit diffraction pattern that you must have studied in optics. And so therefore, what quantum mechanics tells us, and this is very beautifully discussed by Feynman in his book, in the third volume of his book, that an electron, the source is very far away. So by the time the electron reaches the slit, it is almost horizontal. So the x component of the momentum is 0. As soon as you make it pass through the slit imparts a momentum. And the probability, just by confining the electron between a distance of the order of b, it imparts a momentum. The probability that the momentum lies between px and px plus dpx is proportional to sine square beta by beta square, where beta is equal to pi b px h Px is the x component of the momentum, which is p sine theta. And then you write h by p is equal to lambda. So this is the single slit diffraction pattern. The smaller the width, the greater is the momentum spread. And that is my uncertainty principle. So if you work this out, it will require a little bit of patience. Then the uncertainty principle is contained in the solution of the Schrodinger equation. Everything is contained in the Schrodinger equation. I'll repeat, the uncertainty principle, that if you try to localize a particle within a distance of delta x, then there has to be necessarily a momentum spread such that the product is equal to h cross. So the uncertainty principle itself, all solutions of Schrodinger equation are consistent with the uncertainty principle. So what I have told you is the following, that understand this. The electron comes in from the left, then the slit, by confining the electron to a slit of width b, the slit imparts a momentum. And this is the probability distribution is like this. Where will it land? I do not know. No one knows. But the probability distribution is the same as the intensity pattern predicted by the wave theory. And so therefore, if you did the experiment with one electron, it will land here or here or here or here or here. But if you did with million electrons, then slowly the diffraction pattern will build up. So quantum mechanics is probabilistic in nature. Classical mechanics is deterministic in nature. There's a conceptual difference. You cannot predict the future. So David Bohm says the most fundamental theory now available is probabilistic in form and not deterministic. I will give you a very simple example of probability. Let us suppose this is a uranium solid. It has a radioactive substance. It has supposed half-life of say 1 day or 1 year. It does not matter. What does the concept of half-life mean? That let us suppose there are 1,000 atoms or 1,000 nuclei. You say that in 1 day, 500 will decay. But all atoms are identical. Which atom will decay? No one can predict. On average, one atom can live for 1 year or 10 years, and the other atom will decay in the next moment. So in the phenomenon of radioactivity, it is embedded the concept of probability and concept of quantum mechanics. And quantum mechanics allows us to predict the probability. So let me do another experiment. So I have here a double slit. Unfortunately, the figure is not very clear. So for a double slit experiment, the interference experiment, the electron passes through either of the slits. So it is given by a wave function, which is 1 over under root b here, constant here, and constant there, and 0 everywhere else. I substitute that and calculate A of px. If I do that, I leave that as an exercise and square it, I'll get sine square by beta square and cos square gamma. So this is the single slit diffraction pattern, and this is the double hole interference pattern or 2-point interference pattern. So this equation is what is predicted by classical wave theory or electromagnetic theory. And you read that in your optics course. And quantum mechanics tells us that the probability that it imparts a momentum between Px and Px plus dApx is the same as an intensity distribution predicted by wave theory. So I have an electron gun which emits electrons. This figure is taken from Feynman lectures. So I have again a two-slit experiment, and then imagine the electron as a tiny particle. So just like a bullet, when you measure on the screen, you measure either one electron or no electron, never half of an electron, never half of an electron. Feynman says it is detected in lumps. So P1 is the intensity distribution when slit number 1 is open. P2 is the intensity distribution when only the slit number 2 is open. And then you say when both the slits are open, then you must get the sum, because the electron will pass through either hole number 1 or hole number 2. But you do not get that. You get the interference pattern. And this is the interference pattern as I have just now calculated. So before its detection, please listen carefully. It is described by a wave function which is everywhere. The process of detection makes it collapse to a particular point. Where will it collapse? I don't know. No one knows. I can only predict a probability distribution. And this was the most beautiful experiment that I had mentioned earlier in the talk, that this experiment corresponds to 10 electrons, then 100, then 3,000, then 20,000, and 70,000. Slowly, the interference pattern builds up. But they are governed by probability distribution. If you did the experiment with one electron, where will it arrive? You cannot say. So similarly, one atom, one nucleus can decay in the first minute or after 1 hour. So this is the heart of quantum mechanics. The collapse of the wave function. First of all, it is a probabilistic theory. And second, you detect it in lumps. And the third thing is it is described just before it hits the screen. It is described by a wave function which is everywhere. The process of measurement makes it collapse. So Feynman says electrons do not behave like particles. They do not behave like waves. Electrons in orbit are not somewhat like a cloud or fog of some sort surrounding the nucleus. It behaves like nothing that you have seen before. There is one simplification, that electrons behaves exactly in the same way as photons or protons or neutrons. So the two-slit interference experiment for electrons or for photons or for protons or for alpha particles is a phenomenon which is impossible, absolutely impossible to explain in any classical way. That's what Feynman says, and which has in it the heart of quantum mechanics. I'll discuss 2 more experiments. So I have a beam splitter and I have a single photon source, laser. So one photon comes in, one photon. Let us suppose there are 1,000 photons per second. It's a 50% reflector. Then you will say that about 500 will be reflected, 500 will be transmitted. That is a wrong answer. That is a wrong answer. A single photon is reflected as well as transmitted. It is here as well as here. But if you put a detector, then it will be either here or there. It will collapse to either here or there. And this collapse of the wave function is very typical of quantum mechanics. Some of you may have done the tunneling through a barrier. So you consider a particle approaching a barrier, and there is a reflection coefficient and a transmission coefficient. So a single wave packet describing an alpha particle interacts with a potential barrier. There is a small reflection coefficient, say 0.4 reflection coefficient, 0.6 transmission coefficient. So it is here as well as here. A single alpha particle is described by a wave localized here and there. Do you have 10 more minutes? 10 मिनट और है या अभी बंद कर दे?
सर देख लीजिए, अगर आप पॉसिबल हो तो वो 5 minutes में वाइंड अप कर दीजिए, because then there will be this question answer session also, if possible. Otherwise you can take your time.
तो 6-7 मिनट कर लेते हैं,
ठीक
ठीक
है
है?
Don't worry
Okay.
about time.
हाँ जी, बिल्कुल बिल्कुल.
Don't
All
worry.
right. Okay. So now let me do one more experiment. I have, polarizer is a very plastic sheet. I have light from a, say, helium neon laser or a sodium light source. I pass through a polarizer. As you all know, that it polarizes the light. The electric field oscillates. And then you have another polarizer. So there is a cos square theta intensity. So, but if you do it with single photons, so you get an X polarized photon, and the probability of it to pass through is cos square theta. Whether it will pass through or not, I don't know. So these are the actual experiments with the Polaroid. These are actual experiments, almost lossless. And when you cross them, then there is a zero probability. But when it is 45 degrees, then cos square 45 is half. So half the photon will not pass through. It may pass through, it may not pass through. So, as you know, I will take 7 more minutes and then I will finish. So, you have a double refraction crystal. So, a beam enters and it splits into 2 beams. And these 2 beams are linearly polarized. So, when an unpolarized light beam is incident normally on a calcite crystal, it usually splits up into 2 linearly polarized beams. They are both linearly polarized. So 45-degree polarized beams, half the intensity goes here, half the intensity goes here. But if we have let us suppose a 45-degree polarized photon, then it is in a superposition, as has been mentioned by Professor Arvind yesterday. It's in a superposed state. वो यहाँ भी है और यहाँ भी है. Until you have measured a detector, then it collapses to either D1 or it collapses to D2. So this equation, that there is a half probability of finding it X polarized, half probability of finding it in Y polarized. Okay. So this is, sorry, just once more. So this is known as an XY device. This is known as an XY device. No matter what the incident polarization is, it splits into 2 beams, which is X polarized and Y polarized. I rotate that crystal, I can have a UV device. So U is both, all axes are orthogonal to the Z axis. And you can have a XY device, UV device, or you rotate it further. All of them are perpendicular to the Z-axis, sigma eta device. Now, this is a calcium atom which emits 2 photons, which is such the photon polarization of the 2 photons, and that comes from quantum mechanics, are at right angles to each other. If this is X polarized, then this is Y polarized. If this is Y polarized, then this is X polarized. So you see, if this comes out as X polarized, then this will come out as Y polarized, and vice versa. The photons are said to be entangled. The photons are said to be entangled. According to quantum theory, read this carefully. The polarization of the photon traveling to the left or to the right is not known before one of them is measured. Is not known. Theory tells us that they are right angles to each other. And these are the Alice and Bob experiments. If the photon, read this carefully, if the photon going to the left is passed through an XY device and it is found to be X polarized, then the photon going to the right collapses to a state which is Y polarized. तो मुझे इसको measure करने की जरूरत नहीं है. If Alice measures it as X polarized, then it will automatically become Y polarized. This will be, the other one will collapse to a state which is Y polarized. Similarly, if you have a UV device, then if Alice measures it's a U polarized, then the other one will collapse to a state which is V polarized. Whatever happened to one particle would thus immediately affect the other particle, wherever in the universe it may be. Einstein called this spooky action at a distance. In 1935, as was mentioned yesterday by Professor Arvind, Einstein, Podolsky, and Rosen wrote a paper. If a quantum theory was correct, then two particles which are millions of kilometers apart can be entangled in the sense that by determining a property of one of the particles, the property of the second particle can be instantaneously changed. And special theory of relativity forbids the transmission of any signal faster than the speed of light. This came to be known as the EPR paradox, which was briefly mentioned by Professor Arvind yesterday. About 30 years later, experiments confirmed the prediction of quantum mechanics. Namely, Einstein's impossible prediction was in fact correct. Instantaneous changes in widely separated systems did occur. That is, यहाँ पर मैं जब X polarization देता हूँ, तो second particle, second photon collapses to a state which is Y polarized. EPR argued, that is Einstein argued, that if without in any way disturbing a system, we can predict with certainty the value of a physical quantity. अगर मैं predict कर सकता हूँ कि second photon is Y polarized, will be collapsed to Y polarized, then the second particle must have possessed, that is the concept of the hidden variable, must have possessed the measured property before the measurement was carried out. So he said that there must be hidden variables. And as was mentioned yesterday, so we assume that there are hidden variables. I'll take 5 more minutes. Thus, there must exist hidden. So, 2 photons जो है, उसमें लिखा हुआ है. I may not know it, but God knows. But quantum mechanics say even God does not know. It's a very subtle difference. That if this is passed through an XY device, then this will be X polarized. Then this will be Y polarized. If it is passed through a UV device, it is U polarized, then this will be V polarized. If it is passed through a sigma eta device, then it will be, this is what quantum mechanics is. And if there are 2, 3 positions, then there are 8 possible combinations. So you get, थोड़ा सा algebra है, वो मैं reference दे दूंगा. So P of X sigma is the probability that if the left photon is passed through an XY polarizer, you measure X polarized, and the right one is a sigma eta device, and you measure, you sigma polarization. And similarly others. So you get this and you get this. And you can see since this is greater than this is a simple form of what is known as Bell's inequality. देखो, इसको समझ लो. Let me spend 1 minute. I'm sorry, I'm taking little.
Okay, sir, no problem, no problem. Very interesting and informative.
Yeah. So the left-hand side, what is Bell's inequality? The left-hand side says the probability that the left photon is passed through an XY device and you measure X polarization. Then the right side will be Y polarized. But you pass through an UV device, which is slightly tilted, and you find that you measured U. What is the probability of that? And he shows that if hidden variables are assumed, then this inequality will be satisfied. And see that you can calculate this using simple quantum mechanics. If the left-hand photon is X polarized, then the right-hand photon will be Y polarized. And so the probability of measuring U polarization will be governed by the Malus's law, which I had shown, and that is half sine square theta. And then you can similarly calculate others also. And therefore, Bell's inequality will say that sine square theta must be less than sine square phi plus sine square phi minus theta. And if we assume theta is equal to 2 phi, then this is less than this. For pi equal to this, it becomes this inequality. ये बहुत आसान है. थोड़ा सा मेहनत करना पड़ेगा. This is an impossibility. And so therefore, thus quantum theory and Bell's inequality are not compatible. Einstein said that there must be a hidden variable inside the quantum theory. That is the profound result that Bell had obtained. If John Bell died at the age of 60, he was the brightest of the young men. He would have definitely got the Nobel Prize. Thus, quantum theory and Bell's inequality are not compatible, which implies that either quantum theory is right or theory based on hidden variables, but not both. And then there are a series of experiments which were carried out, and the most beautiful and brilliant experiment was carried out by Alan Aspect. This is the cadmium source, calcium source, which emits 2 photons, and this is an XY device, and this is an UV device. And you make the measurement of the polarization. And Aspect writes, the linear polarization correlation of pairs of photons emitted in a radiative cascade of calcium has been measured. The new experimental scheme using 2-channel polarizer is a straightforward transposition of the EPR Gedanken experiment, Einstein-Podolsky-Rosen thought experiment. The present results, excellent agreement with the quantum mechanical prediction, lead to the greatest violation of Bell's inequalities. Bell's theorem is one of the most profound, this is what Zillinger, who later got the Nobel Prize, writes, as one of the most profound discoveries since Copernicus. Bell delivered a death blow to the local realistic picture of the world. Many experiments have demonstrated that the predictions of quantum mechanics for entangled particles are fully correct. So they have been awarded the Nobel Prize. एक experiment और बता देता हूँ. जैसे ये silver atoms है. आपने Stern-Gerlach experiment देखा होगा. So Stern-Gerlach, the inhomogeneous magnetic field spin. You see, what is an electron? Because how do I understand the spin? It has a magnetic moment. It is like a tiny magnet. So you make a measurement of the Z component of the magnetic moment. It is up or down. So you take a spin zero system like something like this, electron and positron put together. You put a spin zero particle composite, and then the electron and positron separate. Since it is a singlet state, it will be a superposition of up, down, and down, up. It's a superposition of up, down, and down, up. So if this measures up, then this will measure down. If this measures down, then this will measure up. So this is also a entangled state, something like that. चलो यहीं पर खत्म करते हैं. These are the books, the very famous books on quantum mechanics. I thought I will tell you all of you. This is by Dirac, Principles of Quantum Mechanics, and of course the brilliant Feynman lectures. Quantum theory by Bohm. Bohm, many people feel that he should have also got the Nobel Prize. And this is by Kuhan Tanuji, who is receiving the Nobel Prize. David Bohm, an outstanding quantum physicist, eventually became a philosopher. Even Schrödinger became a philosopher. And here is Dirac talking to Richard Feynman. And this book was translated by two of my very good friends, Dan and Nicole Ostrowski. And whatever I have done today is given in my optics book and my quantum mechanics book. I thought I will tell all of you that for the last 2 years, I'm getting very old also. I have been working on the 8th edition of optics, and which should come out in a month. And the cover is a photograph of the Aurorus Borealis, the spectacular display of colors in the northern and in the southern hemispheres are called aurora borealis. The aurora can be seen near the north and south poles. The colors are caused by the following process. Charged particles emitted by the sun and trapped in the magnetic field near the poles collide with the atoms and molecules in our atmosphere, and the excited atoms and molecules emit light, which result in the beautiful display of colors. The green color is primarily due to excitation of oxygen atoms, while the purple color is caused by the nitrogen atom. When I see this, I had a great desire to see this, but I don't think I will be able to see this in my lifetime. But I have seen the video clips. When you see such spectacular display of colors, you see God in them. I see God in them. So thank you for. Sorry for exceeding my time.
No, sir, no, it's a very wonderful lecture. So very much thankful from core of my heart for such interesting and enlightening talk, and extend my sincere gratitude to great personality, Professor Ajoy Ghatak. Sir, this lecture has also been streamlined on the YouTube, and more than 200 participants have joined through YouTube. So now let us take a few of the queries of our participants.
And send me the link to the YouTube, then I can see the questions myself.
Sir, I have already sent you that link.
The questions are on this chat box also, but I have written, I can, if you say,
yes, sir, I have sent you.
Say I can, these are on the chat box of this Zoom also. So otherwise I can read one by one and you can give the answer. It will save the time also. So sir, there is one question from Niyar Prabhat. If
I can see the chat box, sorry.
Hanji.
Good evening, please mute. Good evening, especially, I'm really thankful. My name is AJ Uwai, not Ajoy.
Okay.
Good evening, slides are not changing. That's a good evening, clicking on the icon will slide. Good evening. Electromagnetic waves are not mechanical waves. Nayar Prabhat are not mechanical waves. They are not even matter waves, so far as I know. For this reason, they do not need media. So they are electromagnetic waves. They are electromagnetic waves. So that's what I tried to say, that associated, you see, you have a dipole oscillating, it radiates electric field. Now, so therefore, in empty space, you have an oscillating electric field. And Faraday's law says that if you have a changing magnetic field, there will be a changing electric field. And the concept of displacement current says, if you have a changing electric field, it will produce a changing magnetic field. And that is how the fields propagate in empty space. Okay? So they are not, you are right, they are not mechanical waves. Does de Broglie specify just dual nature of particle, or did he say anything photon? No. He just said about electrons. He just said about electrons. Photon ka to sara Einstein. If you are asked in the examination, who discovered wave particle duality? The answer is Einstein. Einstein in 1905 discovered wave particle duality. But what de Broglie said is the following, that actually in France it is produced as de Broglie. De Broglie said was the following, that since the electron, since the photon, the light quantum displays wave and particle nature, electron must also display wave nature. So that was de Broglie's prediction from theory. And you know how he got it? Because he, at that time, Bohr model of atom was there. And he says each discrete circular orbit corresponds to an integral number of wavelengths. I've explained this in my book. And that's how he justified the lambda is equal to h by p. And therefore he said, what de Broglie said was that an electron or proton or neutron to tab discover bhi nahi hua tha. Has a momentum p, it has to have a wavelength associated. So it must also demonstrate wave-like properties. 3 years later or 2 years later, Davison and Germer and Thomson, G.P. Thomson, not J.J. Thomson, G.P. Thomson carried out experiment showing diffraction, establishing, and they calculated the wavelength using the de Broglie relation and established the wave-particle duality for electrons. So therefore, to summarize, who discovered wave-particle duality? Einstein in 1905. He said light was at that time known to be an electromagnetic wave. He said that light must also show corpuscular light quantum packets of energy, which we now call as photons. Then in 1924, de Broglie said that it not only light, but electron must also demonstrate wave-like properties. So the duality nature of electron was predicted by de Broglie, which was verified experimentally in 1926. As we studied monochromatic source produce interference, then why we say electron quantum interferences, electrons have a number of light nature of different frequency, then how this is valid for single light of, it is question, Amar Jyoti ji, I cannot understand. So you can demonstrate the double hole interference pattern build up for single electrons as well as single photons. Ye kiya gaya hai. Single photon source se bhi single electron build up. So you have a single electron coming in or a single photon coming in, interacting with the double slit, then you have a probability distribution, which is the intensity distribution. And if you have one photon, it will collapse from being everywhere to collapse to a certain point. So there are four important concepts associated with quantum mechanics. First, electron is neither a wave nor a particle. It is described by a wave function psi, which is the solution of the Schrödinger equation in the non-relativistic case. In the relativistic case, it is the solution of the Dirac equation. Let us forget about non-relativistic. So that is the first thing. Second, the wave function, when you make a measurement, the theory predicts a probability distribution, as I did for 3 examples. the process of measurement makes it collapse. Where can it collapse? I do not know. No one knows. God does not know. But there is a probability distribution that I can calculate. So if you carry out with n number of with millions of electrons, then slowly the interference pattern will build up. And that is what the most beautiful experiment in science, the 2-electron interference pattern. JS says if an electron also shows a wave-like nature as well as particle, it is paradoxical. No, it is not paradoxical. The point is, it is not paradoxical. The question is an electron shows a wave-like as well as particle-like. So the answer to that question, as I repeatedly said, it is neither a particle nor a wave. So kya hai? I do not know. No one understands quantum mechanics. How that electron passed through both the holes at once, no one understands. Not that I do not understand. That's why Feynman said that no one understands quantum mechanics. But I can calculate the probability distribution. So there is a very famous sentence. Don't ask too many questions. This is not me. Don't ask too many questions. Shut up and calculate. Because quantum mechanics is one of the most successful theories that has ever been put forward. Okay? Something like that. According to Feynman, electron is neither a Manoj Kishore. It is if Feynman electron is neither a particle nor a wave. Why should we start describing it by a plane? Oh, that is the thing. There is a flaw there. So I made a heuristic. The word heuristic means इसी तरह से I have to appear at this equation. वो rigorous derivation नहीं है. वो rigorous derivation नहीं है. And many people may just start. I start with this wave equation. So I made a derivation, but that is far from being rigorous. Oh, that is a valid question. Dr. Sangeeta Prashar says, how momentum can take the negative infinite value? So that is right. It does not. But it is not from minus infinity to plus infinity. Can I say, integrate ho jata hai. Actually, you are right. It cannot exceed the velocity of light. You are right. Someone asked if it is neither particle nor wave, what it is. I don't know. Not that I do not. Srishti Yadav. She asked, I think it's a she, that someone asked if it is neither particle nor a wave, then what it is. I don't know. That's why Feynman says that no one understands quantum mechanics. But I know I can calculate what will appear on that photographic plate. Okay. No, some people wanted that I should continue. It's interesting. Chalo, antiparticle. No, even the positron, it's neither a particle nor a wave. But positron ka lifetime बहुत कम है. Do single photon, देखो, single photon interference experiment. Yes. You see, when you pass through a single photon or a single electron or a single proton through double slit arrangement, that is why double slit experiment contains the entire physics of quantum mechanics. It passes through both the holes. How does it pass through both the holes? I don't know. But the wave function, quantum mechanics tells us that don't ask how it passes through, but it passes through both the holes at once. If you make a measurement, then it will be either here or there. Then it will collapse being either here or there, and that process of measurement will disturb the system and the interference pattern will be washed out. So I can just 1 second. So now let me quickly go through the answers to just 1 second. Let me go through quickly to the नहीं, मुझे वो नहीं मिला है, लिंक टू दी यूट्यूब, लिंक टू दी यूट्यूब नहीं मिला है। ईमेल आपने किया था, मुझे मिला नहीं है।
बट
Sir,
सर
I have
चैट बॉक्स में है सारे क्वेश्चंस।
sir, I
क्वेश्चंस
have
आर इन द
sent you
चैट
a WhatsApp.
बॉक्स।
Sir, I have sent you a WhatsApp number. I
व्हाट्सएप
have
पे
sent
कहाँ
you.
होगा, आप मुझे कंप्यूटर में भेजिए ना, लैपटॉप में एक दफे भेज दीजिए, ajoy@gmail.com। Oh, I got a message from Neetu. So she is listening. I'm so sorry to hear that you are not well. But कहाँ है? Can you send me the, then otherwise let us finish here. ठीक है? चलो इसको मैं फॉरवर्ड कर देता हूँ। Just one second. I don't know. I am little novice in. I can't use this cell phone too many times. I find my laptop much better. So I forwarded my this thing to my laptop. Let us see whether it comes or not. Just one second. हाँ, ये आ गया। अभिषेक मिश्रा ने भेज दी। ये क्या हो गया? चलो छोड़ो। ओहो, wave particle duality, Manisha says, given by Einstein. So let us. So I have answered most of the questions. ठीक है, चलो यही खत्म करते हैं. Okay.
Thanks, sir. Thank you very much for answering all the queries of all the participants. Handful thanks to our honorable resource person, our mentor and guide, Professor A.K. Ghatak, for providing quality time and to share his ideas. On behalf of IAPT RC2, I am thankful to dynamic, energetic lady, Principal Professor Dr. Atima Sharma, and President IAPT Professor P.K. Aluwalia, who are the inspirational soul for this workshop. Thanks to all the participants for patience listening, and we all have enjoyed the talk, and we can say that we have absorbed many facts. So members of IAPT हर समय कुछ ना कुछ नया कर गुजरने के लिए तत्पर रहते हैं। उनके लिए मंजिलें उन्हीं को मिलती हैं जिनके सपनों में जान होती है। पंखों से कुछ नहीं होता, हौसलों से ही उड़ान होती है। हौसलों से उड़ान होती है। और एट लास्ट जाते जाते घटक सर आपके लिए वो आए ऑनलाइन प्लेटफॉर्म पर हमें क्वांटम से रूबरू करवाने। कभी हम उनको तो कभी अपनी ऑर्गेनाइजेशन IAPT को सलाम करते हैं। Thank you very much. Thanks a lot. Thanks to all.
May I take 1 minute? With
Sure,
your
sir,
permission?
sure.
Yeah, good evening, Professor Aluwalia.
I enjoyed your lecture. It was a treat, sir. Such a
अरे
wonderful
देखो,
lecture you have given. And I think there must have been many doubts which must have been removed from the minds of the listeners. At least that is true in my case. And I saw one thing very interesting. that now, sir, whenever quantum mechanics will be taught, people will definitely go right in the interpretation of wave function to entanglement. They will start teaching entanglement now.
Yes.
It is the best part of it. And sir, congratulations for your new editions of the books, which are almost now classics in India and abroad because of the translation. And
मैं
I
उसका
think
कवर दिखाना चाहता था आप लोगों
सर
को
कवर देख के बहुत अच्छा लगा सर। हम आपसे बिल्कुल बात भी करेंगे उन किताबों के बारे में, और आपने हमारी रिक्वेस्ट एक्सेप्ट की, और इस प्रोग्राम में आप ने इतना बढ़िया लेक्चर दिया, सभी सारे के सारे कहते हैं ना सर, मंत्र मुग्ध, आपने मंत्र दिया सबको। And I think, sir, IAPT has been encouraged a lot by your presence in various other programs which we conduct. When you come, it encourages us. And we are grateful for your presence. And, sir, this program particularly has been a kind of a gate crashing kind of a thing. We do not have so many, members who can come on the Zoom platform, but on YouTube also there are a lot of participants. So today there were in all around 300 participants who heard your lecture, sir. And thanks to the technology, thanks to quantum mechanics, which has given us this technology, that we are able to do all these things. From my core of heart, sir, I once again thank you, and on behalf of IAPT as well. And we will keep on looking forward to your presence in our program. Let me
Sir,
tell participants one thing more, sir. That this month we are going to have a lecture by a Nobel laureate on 17th of April. And that is on physics education research. It is by Carl Wieman, who actually experimentally created the Bose condensate. So we will. So he will be coming, and we would love to see you in that lecture.
Certainly.
Kind of a prior information to the participants also. Thank you, Meenakshi ma'am, for conducting this, and I wish ma'am Neetu a very rapid recovery.
No, I got a message. I got a WhatsApp message.
Yes, she was watching actually.
Sir, despite her health conditions, she was so excited to listen, Dr. Saab talk. And she personally called me and said, you should take care of all the things. And definitely, I messaged her also that all went well. So she is now relieved. She was taking care of each and everything. So on the behalf of our head of the department, Dr. Neetu Verma, I would like to extend vote of thanks to all of you. Thanks, ma'am, Meenakshi ma'am. You used to come to our college, and very much thanks to Professor Ahluwalia, who provided a legendary speakers. Yesterday Professor Arvind lecture was so mesmerizing, and he taught about some quantum entanglement in terms of twin brothers or twin sisters. That was very interesting. So Professor Ahluwalia, you do always provide such a legendary speakers in coming events, and we have now a memorandum of understanding with you officially also. Right?
I think
तो
IAPT
सर के लिए तभी तो है ना कि मंजिलें, ये सर के लिए ही तो है कि हम सबको दिखा रहे हैं मंजिलें उन्हीं को मिलती हैं जिनके सपनों में जान उठती है, पंखों से कुछ नहीं होता, हौसलों से ही उड़ान उठती है। सर के हौसले हैं जो हमें आगे उड़ा करके लेके जाते हैं।
So nice to hear you. I wish my prayers are with Neetu Verma.
Thanks.
And I'm so, I feel bad that I could not see her on the dais, but let her get well very soon. And my best wishes. And thank you so much, Ahluwalia ji. You have been a source of inspiration to all of us. And Professor Khandelwal was not my teacher, but he joined. I was a student at Agra College. When I left for my MSc, he joined as a faculty there. So in a way, he was my teacher. So that the IAPT is due to him, due to his vision. And he would come to IIT and will speak about so much about IAPT. And I'm so happy that you are taking it to such great heights. Thank you.
So now, sir, we will sign off. Thank you very much.
Thank you.
Thank you, sir. Thank you, Ji. Thank you. Thanks to everyone.